Hi everybody. Today we're going to look at on the Raspberry Pi how much processing power does it take to output the PWM signals that we use to drive the motors on our mobile robot. Pardon the noise, but I have a 3D printer running right now and it's going to make a little bit of noise in the background. Now here on our Raspberry Pi we have 4 channels that are occupied on the GPIO pins that are currently using software-based PWM outputs to drive the signals going to the motor driver. The motor driver basically interprets these signals in pairs with inputs 1 and 2 corresponding to outputs 1 and 2. That's not hooked up right now, but what it'll do is give me something in between positive 12 volts to 0 to negative 12 volts going out to my DC motor to drive it forwards or backwards. Well, as it turns out, these motors are they run a lot better with less noise and more efficiency, and you will reach the spec torque only when you output a decently high PWM frequency on these channels. And so that means we're going to be asking the processor of the Raspberry Pi to generate using software the rising and falling edges on these 4 outputs, which means you have demand on your processor of 4 signals times whatever frequency it is that you're asking for. So let's look at the software and try to take a look at how much this will ask from our processor. So here on my computer I connected with the terminal to my Raspberry Pi, and I'm going to run a program called L1motor.py. Let me open it up first using Nano, and we can see that I have 4 channels being output, left and right times A and B, and the frequency right now is 15,000. So the default frequency where we started with, or something suggested by an example program, is fairly low at 150, and this is where we don't get the best performance out of the motor. So I'll save this. I'm going to exit now and I'll run it. So Python 3 L1 motor, and then I'll come back to my other terminal connected to the same computer, and you can see if you type in htop you can check the processes that are running. So we have 4 times this process, the Python 3 L1 motor.py, and they bounce around in the sequence, but essentially we have the CPU being consumed at 3.3%, 1.3, 1.3, 0.7. Okay, it's a changing number, but I took a screenshot of this and then I varied the frequency of these of the motor driving, and then I took my screenshots at different frequencies to check. I should note that we have 4 different bars corresponding to the processor, so maybe there are 4 threads that can run on my version of the Raspberry. This one, it happens to be the Pi 3B Plus. So for my results, I added up the percentages by each of them, and what I got was pretty interesting. And keep in mind, this is a crude kind of experiment, but it's just to get an idea. At 150 hertz of 4 signals, we were only using a total of less than 4%. At 1500 hertz, which is kind of minimal in my experience, to get the motors to start sounding smooth, and when you grip them while you're giving them a 90% duty cycle, you grip the motor and you can feel that it's giving you a nice torque. Not so much true at 150 hertz or at 50 hertz. This is using 23% of the processor. Maybe that's actually 23% of 400, but still very significant, and I would potentially want to go up into the kilohertz region, like 15 kilohertz. In that case, you've consumed what totals to be 108%. This is what it looked like. Python 3 is up here in the CPU, 29, 24, 23% consumption. So I would be interested to learn more precisely what these numbers mean and what they correspond to, but you can notice when you're running a program that the response of other parts of your program don't always go as fast when you're running the motors at a higher frequency, and that's a pretty major drawback. So our next step is to take this and use outputs 12 and 13, which correspond to actual hardware-based PWM cycles, and then we're gonna run a daemon and tap into the hardware capabilities, and at least convert 2 of our signals over to hardware. And I'll publish a video when I can get to that.